This is image editing with linear algebra, using it to apply filters and add other effects to images.
What's your name?
I'm Felicity.
And I'm Oscar. In this presentation, we'll be using matrices to apply basic filters and use kernels to blur and sharpen images. The first image function that we'll be looking at is flipping images. We can do this by multiplying the image matrix by the reverse identity matrix, which is essentially the identity matrix, but with the ones along the opposing diagonal, not the main diagonal. And when we do this, the image gets flipped along its vertical axis, so it looks like a mirror image of the original.
Interesting.
As our first example, we can see Bingus on the left is a normally facing Bingus. For simplicity's sake, we're using black and white images for all of these. Multiplying it by the reverse identity matrix, naturally it would not be a 3x3 and it would be the size of the image, results in a Bingus flipped around the y-axis facing the other direction. Next, we'll be discussing brightening and darkening images. This is a pretty basic function where we can add an m by n matrix the same size as the original image to the image to result in a lighter or darker image, depending on if we're adding or subtracting it here. Here, for this first one, you can see that we have our original image, which is just made up of randomly selected values. And then once we add 50 Shades of Gray to it, we results in a lighter matrix all around where each value has 50 added to it. Here you'll also notice that some values, like this first 250, only goes up to 255, and there's many ways you can represent black and white images, but we chose one of the more basic ones where 255 represents a perfectly white pixel, black represents a 0 perfectly black pixel, and everything else is in between. So 255 and 0 make up a floor and ceiling where values can't go above or below that, and that's just a very basic way to represent images. And then here you can see we're darkening the original images by subtracting the matrix, which results in a darker image all around, and you can see several values that were going to go below 0 stopped at 0 and just became black pixels.
We see here an example of brightening and darkening images using Bingus. Up on the left, we see the original image, and when we brighten it, we see it looks almost as if a lighter film was put over it, where the lightest part of Bingus, his forehead, still stays pure white, and the background becomes a slightly lighter shade of gray. In the darkening image, we see the background, which started as pure black, still stays pure black and doesn't change, while the rest of Bingus becomes darker shades of gray. Next, after looking at adding a matrix of all the same value to an image, we're going to look at adding two image matrices together. We have a very basic example here where we just have black and white pixels, where black is still 0 and white is still the value of 255, with those being the floor and ceiling. So when we add these two image matrices together, we see when black pixels are added together, they stay at the value of 0, which is black. When white pixels are added together, they still hit that ceiling of 255, so they stay white. And when a black and a white pixel are added together, they become white with the value of 255. So adding these two images we see on the right together, we get this image on the left. Similarly, with subtracting image matrices, if we start with a black pixel and subtract another black pixel, it stays at 0 and stays a black pixel. When we subtract a white pixel from a white pixel, those values go to 0 and it becomes a black pixel. And when we subtract a white pixel from a black pixel, while that would go to negative, in this specific case, we have the floor of 0, so it also becomes a black pixel.
Here we're using a flower overlay over Bingus to represent adding the flower to Bingus. We also darkened Bingus to dramatize the effect. So to begin with adding the flower to Bingus, we can see that the outline of Bingus, all of the white space, will stay white because naturally, if that value is 255 and you're adding more to it, more color from the flower, it'll stay white because of the ceiling. Also, because Bingus starts at a generally low value, the flower you can see on the right will start to appear in the image because you're just adding the flower to a relatively dark image to get a semi-decent overlay of a flower. Now for subtracting images, you can also see that starting in the background, you'll take the white Bingus background, and then subtracting a flower still shows the flower, but in a reverse color. And that naturally, as you can think, if you were taking the white background and subtracting a high value flower petal, would result in a very low value, whereas the background of the flower, the water, is a relatively low value to start, so subtracting that from the white background stays pretty high. And that's why the color is flipped. As well as on Bingus, you're starting with a relatively low black pixel color, so subtracting a relatively light flower petal color from that would go to black. And that's why you can see the black outline of Bingus on the right. Kernel Bingus is now sharpened. Find out what this means in a moment. Here's the very basics of kernels. So a kernel is generally represented as a 3x3 matrix, though they can be bigger. This is a popular size. Here is a very basic kernel, just all ones, and this represents a very basic blurring effect. So to implement a kernel onto a matrix, we take this original matrix, 5x5. We'll pretend these values inside are values representing colors, but they're very low for simplicity's sake. To begin, we take this first 3x3 box here and multiply the kernel by the 3x3 box. So we'll take 1 times 1 plus the second 1 times 1, so on and so forth, until we add them all up together, and we'll get 13 from that. Because we want this to be a blurring effect, we'll average it by the size of the kernel, which is 9. So in this first box over here, we'll put 13 ninths. We'll do the same thing for this second box right here, where we'll scoot it over 1 to the right and do the exact same effect where we multiply the kernel by it. And that results in 19. Naturally average it again, divided by 9. And we'll keep moving until we get to the end of the row, then move down 1 and do the next 3x3. And we'll do that all the way until we get to the end. Now you may notice that the resulting matrix is a 3x3 from the original 5x5. There are ways to account for the edges so that it stays the same size, but this is the simplest manner of going about it. And in a bigger image, removing the edges is not a very big deal, as it is with a 5x5 matrix.
Another way of blurring an image using kernels is using the Gaussian blur. This is just a much more popular and effective blurring technique that looks better on images. Some other very basic kernels are shown below. On the left, we have a kernel to sharpen images, as we saw used on the previous Bingus. This just makes images sharper and clearer. Next, the outline kernel, it can be used to give a sort of outline effect on an image, where pixels that are between light and dark values get highlighted and emphasized, and it basically looks like an outline around an image. Finally, the emboss effect is used to give a sort of stamping effect. It also uses some outline components, but it is based off of what it looks like when a paper is stamped.
Now we will look at some Binguses under these different kernels. First, here is an outline Bingus, where you can see the very edge of Bingus has a very distinct white outline. Next, we have two different versions of embossed Binguses, where you can see that the texture almost looks like a paper, as if it were stamped. Finally, here's a side-by-side of the original Bingus on the left versus the sharpened Bingus on the right. And you can very clearly see how some features around the edges look much sharper than before.
Thank you for listening to our presentation. We hope you learned lots about image filters using matrices.